Hi, thank you so much for having me. I have to apologize, I have a bit of a cold, so if you find me diving behind the stage, it's because I have to sneeze, but I'll try to avoid that. So I'll tell you a little bit about my research work at Arab that I've been working on part-time for the last couple of years. It will be illustrating our design process, mostly a lot of the failures that we made, because I will hope that it will inspire you to try it out and to look into the possibilities of additive manufacturing. Am I clear? Can everyone hear me in the back? Yeah, okay, cool. Let's see if this works. Yeah. So how did we get started? As some of you might know, the building industry is quite a conservative industry, I'm afraid to say. But we at Arab, and I've been told that a lot of you guys probably know what Arab is. So it's an international engineering firm. We work at pretty extreme structures and buildings and infrastructure. But even though they're quite innovative and extreme, as I said, it's still a conservative industry where a lot of traditional materials and traditional production techniques are being used. Me and my colleagues were working on this tensegrity structure for years. It might not be built in the end. Everyone is asking me about that, but probably not. For the people that are not structural engineers, a tensegrity structure is actually quite a simple structure, at least the idea behind it is simple, because it consists of tension and compression elements, cables and struts, and those sort of forces are in perfect equilibrium with each other. For this project in The Hague, a city in the Netherlands, it was actually super fancy street lighting. Normally, a tensegrity is built out of modules that are either stacked on top of each other or placed next to each other. Our architect wanted to have more of a blob-like structure, as you can see here. And that was fine for us to design and calculate and prove that it would work as a structure. What was a little bit more difficult for us is to design for manufacturing, or at least that was what I thought. My background is product design, so I'm used to come up with one design that's then produced many times over. But the solution on this project of our structural engineers was to create these nodes. And the nodes are just elements connecting the cables to the struts, so the tension to the compression elements in this structure. We had 1,600 of those. The structures were quite relatively small, but 1,200 design variations. So the solution on the project was, okay, we're just going to make those 1,200 different CAD drawings, send them over to the contractor and expect them to be produced by hand. These elements, you see a skilled model here, but are 0.5 meter tall and were required all the different elements to be cut in unique shapes and welded by hand together, which is a bit of a production nightmare. But it was the inspiration for the research that came up, because I was thinking there must be production techniques out there that actually allow for mass customization or uniqueness. And that's how we started looking at additive manufacturing. Very briefly, for the people that are not really into the subject, we're looking at metal here, and the way it works is actually quite simple. You have a printer or a machine with a building chamber in it that is a certain size. It's relatively small still at the moment, unfortunately. You feed a digital 3D model in there that's been sliced in very thin layers. The printer puts a very thin layer of metal powder in the building chamber, and a laser actually melts the powder where it should become part of the solid product. The rest of the powder just stays powder. Then a new layer is put on top, welded or melted again, and in this way a product is built up from scratch. The reason we actually dared looking at this technique is that in other industries like aviation and aerospace, they were already years ahead of us, and they were already using this technique to build motor parts or pieces of airplane wings or whatever. So my reasoning was that if you can build a part of a motor that's high quality and has a lot of requirements to it, we might as well build structural elements. But at the time, my colleagues didn't really agree with that. Still, we got the chance to look into it, and we had no idea what we were getting ourselves into. We had no idea how to design for additive manufacturing. But what we did know is that we were not going to print the exact same shape that we had before, because that one was designed for more like traditional production techniques. So we tried to analyze the function of this node and describe that in sort of design rules. And then we thought, okay, we have this element connecting things together, but we're going to print it from scratch. So we actually have a choice of where exactly to put the material. And a lot of people think this first one, the original design, looks very robust and strong and a real structural element. But actually, there's a lot of material in there that we really do not need. So we used, at the time, within software to do a topology optimization in which the computer checks for each particle in a certain volume whether there are actually forces being applied to that, so whether you need material to it or not. Well, that all went pretty smoothly, and we actually had a result that looked different than the original design, so we were very pleased with ourselves. And we went to the production company, because we're not producers ourselves. We said, can you please print this for us? And they said, yeah, sure, but it's not very easy to print. And then we actually learned about the design rules that are related to additive manufacturing. Everyone has been telling us that you can print everything you want, so we never took any design rules into account. You couldn't also really find them on the internet or something, so we were a little bit surprised and of course disappointed, but we said, okay, we better learn about these. And one of the rules that you might want to know about is, for example, horizontal surfaces. I just explained to you how the process works. As you can see here, this shows the physical product, but you can also see the orange, or some of the orange parts actually sit on top of a very thick layer of powder. You can imagine when you have a thick layer of powder and you start to weld or melt a part that should become part of the solid product, it sits on top of all this powder. And actually that's not very good to get the shape and the size of the product exactly right. There are quite some other rules as well. I won't bore you with that, but keep in mind horizontal surfaces or overhangs is difficult. So what we did at the time when we learned about these design rules is to adapt the product. Because here's what you see can happen. You can actually print a lot if you really want to, but on the left picture you see the support structure that you then need to actually support those surfaces I was just talking about. We really didn't want that because we came from a production process that was already very difficult, so we wanted something that was a lot smarter and quicker, preferably. So we did an analysis on the first design. All the red parts you see are the parts that we actually want gone. So we did, but we didn't really have the right software for that. So I had a very fantastic colleague called Shibo Ren adapting the digital model by hand to make sure none of those horizontal surfaces were in there. And then we finally went to production, of which you can see some of the pictures here. On the left, one of the layers being melted, and in the middle and to the right, the product sort of emerging when the metal powder that's not been used is taken away. Well, pretty nice result. Everyone was really happy about it. Luckily, also some people in the building industry and also the additive manufacturing industry sort of warmed up to the idea of 3D printing for architecture or for the building sector. So everyone was quite enthusiastic, but we saw a lot of the things that we did wrong during this process. We started off not having a clue where to go, and we learned a lot, but we really wanted to give it another try. By the way, if someone already wants to hold or pass through the models, you can just pick them up, that's fine. They're heavy, especially the first one. So, we started over, and this is where it becomes really interesting for us, because what we did with that first try is we isolated the model from its environment, because it was so complex for us, we didn't really know what we were getting ourselves into. We isolated that node and we treated that as a separate element. But we realized during the design process that you can optimize a solution even more if you treat it as part of a bigger system. So that's the start of our second try. So besides uniqueness or mass customization and weight reduction, we now also focused on the integration of different elements of the system. What you can see on the right is elements we originally had to connect the cable to this node, a pin and fork connection and a spanner to keep the tension in the cables. But we said if we're going to print this node, it's going to be complex anyway. Maybe we can make it even a little bit more complex and try to integrate those functionalities into the node as well. And we did, and it actually led to a super simple solution. But as some of you might know, the most simple solutions are often the most difficult ones to come up with. I'll show you the results in a bit. And what we also did is we looked at the effect of the weight reduction on the total system. As you've seen, this structure is only a structure. It's not, you can't really compare it to a normal building structure where you also have facades and windows, etc. But because the nodes are a relatively large part of the total structure, and the weight was going down so much, actually all the other elements in the system could also be made slimmer or thinner or lighter. So the cables could become thinner, the tubes could become lighter. So by taking the weight reduction into account, the system as a whole actually became almost 50% lighter. And if you imagine that some of these urban chandeliers, as we called them at the time, are being hung from buildings in the street, we might have gotten to a point where we didn't have to reinforce the buildings anymore in order to hang the structures from the buildings, which is a massive reduction in cost. But only this to illustrate that looking at the bigger picture is often a good idea. So again, an optimization process. This time we used Altair software because we figured out that within is actually better to use for lattice structures, but that's a whole different story. Finding out the boundary conditions, so actually telling the computer what to do or to find a solution within which space is quite complex. I must say I was quite happy with it. It would have been sad, I think, if we would have come up with a solution where with one push and the button, the computer would do everything and the engineer or designer would not be necessary anymore. But that's definitely not the case. I think the designers provide the basic points of departure, the boundary conditions, the envelope, you could say, and then the computer does the boring work. So I think that's a great deviation of task. And what comes out of it is often very unexpected. I don't think we could have come up with this shape as being the most optimal solution, so that's always exciting. We did have to do some cleaning, a lot of cleaning. Actually, this is where we definitely see a software gap, by the way. We don't think this whole design process is yet properly supported by software, so we're talking to different parties about that. But what we did design in were the interfaces to the other elements, so the interfaces to the cables, the interfaces to the strut, and to the lighting fixture that's also in there. And again, we had to adapt the model for production, so we had to make sure it could actually be printed without or with a limited amount of support structure. And this is the result. I got quite some time left. The same function, completely different shapes. A lot of people like the middle version, but I'm not sure if you were here for the morning session where we talked about cars and autonomous vehicles. The middle version is like a slim version of the original, but I think it becomes only really, really interesting and you can really start optimizing when you approach the solution not as a redesign of the original, but as a completely new approach. And I think this is what illustrates that quite good. I think what's interesting is the shape. It's quite round. Not everyone likes the shape, but we didn't beautify this at all. If you're an architect, if you're a designer, you don't like this kind of shape, you can change it, of course. But we kept it purely functional because we're an engineering firm. We leave a lot of the aesthetics to architects and designers. Purely functional. So what you can see, and please pick up the model also afterwards if you want by hand, that the inside, where the tolerances are very important, you can see it's very clean and clear and very detailed. The outside, where it didn't matter so much, can be more rounded. So this might be interesting for you to see in the model. And I think this picture illustrates better where the shape is coming from. If you see it separately, it's like this super strange blob. But if you see the connection to the cables, then it actually starts making more sense. And I think I still owe you an explanation of our new approach. So where at first we had these pin and fork connections and spanners and all these separate elements to connect the cable to this node, now we just guide it through and connect it with a nut, and that's that. So all the functionalities of those separate elements, the pin and fork and the spanner, are now integrated in this solution. And that's allowed us to eliminate 15,000 products from this particular system. So products that we don't have to order, transport, install, and maintain. And that in itself was also quite a nice benefit. Obviously, it's great that we can design it and that we can print it, but for us it has to work. So, just for your information, we also checked if it would structurally work, so if it would really be strong enough to carry the loads that were being applied to it. So this is a digital check. But we also did a material research because obviously we had material specifications that told us, well, this material is this strong and after printing it can really take on these forces. But we didn't have any experience whatsoever. So we don't think you can build a building based on material specifications made by someone else. So we did our own initial tests, and our metallurgists from Arab, and they're quite specialized and good, I've been told, actually really think that the results of that are pretty good. And as it says here, in accordance with normal products used in the building industry, which is for us very, very important in order to convince other people that this might be a viable technique. That's it. I didn't have to sneeze. Fantastic.